Can I have your attention? Today we have a special departmental seminar. Every year, earlier on, I think most of you know we have a Board of Visitors meeting in which people who are representatives of industry come and have a connection to the Department of Chemistry. They come and they visit at our invitation. During that time, it's usually about a two-day visit. We also have a graduate student poster presentation. Anyone who wishes can submit a poster, and during the visit of the Board of Visitors, they break up into groups, and they come around to each poster and listen to a very short 5 to 10 minute presentation about the graduate work that the poster presents. Okay? And then Board of Visitors reconvenes and they decide on who has given the so-called best presentation. There's always a number of very good ones, but this year, Curtis, Anderson, and Wade were the winners. And so they are given the opportunity to then present their portion of their graduate work at the last departmental seminar of the year, that being this one. So today we will have two presentations. They'll run about 20 minutes each. Curtis works for Dr. Long. Unfortunately, Dr. Long is on a plane coming back to chemistry at this very moment. He asked me to fill in. I'm on Curtis's graduate committee. Let me give you just a short introduction. Curtis grew up in Georgia. He got his undergraduate chemistry degree from what was called Southern Polytechnic State University at the time. It's now called Kennesaw University in Marietta, Georgia. He worked in both, let's see here, both forensics and biochemistry research while at Kennesaw. He then joined Dr. Long's group and is obtaining a PhD in inorganic chemistry, although he's basically doing a lot of polymerization and developing catalysts for making polymers. He's already the first author on 3 publications, and then he has a couple of others that he's co-authored. So without further ado, Curtis, congratulations, and look forward to hearing the presentation.
All right. Thank you, Dr. Barnes. And thank you all for being here today. As he mentioned, I'm in Dr. Long's group, and it is primarily a polymer group, but as he also mentioned, I'm an inorganic chemist. So I focus more on the catalyst development side, and specifically catalysts for the polymerization of ethylene. And so before I get into any details about the catalysts, it's important that I tell you why the polymerization of ethylene is important and why we even choose to study it. So if you take a look at the figure on the left, this represents the entire polymer production for the US for 1980. And as you can see, this 86% here refers to the commodity plastics. These are things such as polyethylene and polypropylene. These are common commodity plastics that everybody uses on a regular basis. And only about 14% and then less than 1% were used for other plastics such as engineering and high-performance plastics. It was envisioned that by 2012, the high-performance plastics and the engineering plastics would be a significantly larger portion of the polymer market due to advancements in processing and engineering and the cost of being able to produce these polymers. However, in reality, the commodity plastics maintained their dominant position for the plastics industry, and they even grew by about 2%. And this is because the overwhelmingly cost-effective polyolefins such as polyethylene and polypropylene were able to then, and as well as the advancements that we had in engineering and processing and the research behind them, were able to maintain their dominant position here. Specifically, over 31% of these commodity plastics is just polyethylene, just the single polymer. And as I mentioned before, this is used for things such as garbage bags or hard hats or even milk jugs, just because it's so, and people come into contact with it every day and they don't even think about it. So currently, these polyethylene is produced via a group 4 catalyst, which is titanium or zirconium, something like that. And I use this metallocene in the middle to represent this. And when it's combined with MAO, which is an activator, and then ethylene, the monomer, you get linear polyethylene chains, which ends up being a very hard and brittle material like the hard hat that I have shown. Now, in order to get something that's more flexible, like this squirt bottle that's over here on the left, you have to add in these expensive comonomers that create branching in the polymer chain. And that is represented by these blue monomers here. And this significantly increases the cost of production. Now, in our lab, we research group 10 catalysts, which are nickel and palladium-based catalysts. And we choose to do this because these group 10 catalysts, when combined with MAO and ethylene, can create any wide variety of different polymer architectures, ranging from high-density polyethylene, which is like the hard hat that I had shown before, medium-density polyethylene, which is slightly more flexible but still a pretty rigid material, all the way down to low density, very low, and then ultra low density, which is something similar to the adhesive type structure that I have shown. Now, the only difference in terms of the architectures here is the increasing amount of branching that exists between each one of them. Now, to understand how these group 10 metals can actually create all these different materials and using only the single feedstock, we have to actually look at the polymerization mechanism. So this standard mechanism is followed by both the group 4 and group 10 catalysts. And essentially, the catalyst is activated using MAO, which is methylaluminoxane, which will create an alkyl chain, a cationic metal center, and then an open coordination site. Now, at this open coordination site, the ethylene monomer can then coordinate, and then through a migratory insertion, it will insert and begin growing a polymer chain. And through repeating this process multiple times, you'll end up getting these very long linear polyethylene chains. Now, group 10 catalysts actually have an alternative pathway available to them, where at any point during this polymerization, they can actually undergo a beta hydride elimination to create the alkene coordinated species here. And then by doing a 2-1 insertion, create essentially the methyl branch, the first branch of this polymer. And it can continue what's called chain walking down this polymer chain, or it can reinsert ethylene and then leave it as a methyl branch there. And this can happen to any degree, which is where you can get methyl branches or branches that are significantly longer than that. And all of these can drastically affect the polymer characteristics. Now, there are currently only really 2 methods that are used to control this chain walking mechanism, and the first of them is pressure. And if you take a look at the example I have here, as you increase the pressure, you tend to get a more linear structure, which is the harder, more rigid material. And as you decrease the pressure of ethylene, you get a more hyperbranch structure. Now, in the Mark-Ewing plot, which is something that we use to represent this, this essentially just shows us that the line towards the top left here represents the more linear structure. And as it moves towards the bottom right, we're getting a more branch structure. That's essentially what this means for our purposes. The other method that we can use to control chain walking is temperature, in which from the proton NMR I have shown here, this very large peak corresponds to the protons in the backbone of the polymer chain. And this very small peak to the right that continues to grow in represents protons that have appeared on branches off of that backbone. So as we increase the temperature, we can also increase the branching. Now, both of these methods are external controls. And in our lab, we wanted to know if there was a way that we could actually bias the catalyst itself to prefer either this mechanism that would lead towards more linear, more rigid polymer, or if we could bias it towards the chain walking mechanism. Now, we drew inspiration from a report in 2005 by Guan and coworkers, where they showed that if you put electron donating groups on the pendant arrow rings of these palladium alpha diamines, or electron withdrawing groups, such as the nitro groups here, you can essentially perform the same sort of control in which you create more or less branching. Now, this was, a very interesting report, but having to synthesize a discrete catalyst each time you wanted to synthesize a type of polymer isn't exactly ideal. We wanted to figure out if there was a way that we could somehow oscillate in between these two states using a single catalytic species. So, our objective was to create a redox active catalyst, which is essentially a catalyst that you can add or remove an electron from, to or from, and this would change the polymerization behavior somehow. So in part one of this talk, I will explain how we took a known catalyst and were able to modulate its redox character, and then by doing so, we were able to create two different polymer microstructures. Part two, I'm going to explain how and why this system worked, and specifically what this reduced catalytic species looked like. In part three, I'll use the same catalyst system, and we use this to change the rate of the polymerization for larger olefins, as well as their comonomer incorporation rates. And then finally, we used this, everything that we had gained from parts 1, 2, and 3 to try and improve the system and try and design our own redox active catalyst. So for part one, the first step was obviously selecting which catalyst that we were going to use. And so the original, this catalyst that was developed in 1995, this is one of Brookhart's original catalysts. And we found a report from 2004 that showed that the ligand that was bound to it was actually also redox active. So we thought, well, I wonder if the catalyst itself is still redox active once it's been metallated with nickel. And so we took a CV trace of this catalyst and we obtained the curve on the right. And this peak here corresponds to a reduction potential at about negative 0.8 volts, which indicated to us that it in fact was redox active. So following that, we then began polymerization trials. And we polymerized ethylene and using this catalyst and MAO, and we obtained this GPC trace for that polymer. And then we repeated the same trial using the catalyst again, but this time we used cobaltocene, which is our reductant. This is what adds our electron to the system. And we essentially got the same GPC trace. And when you analyze the other results from it, the yield was about the same, the turnover frequencies were about the same, as was the molecular weights. So all in all, none of this really told us whether or not these two polymers were actually the same polymer. So we took proton NMRs of these polymers, and we found that as a function of reductant, as we increased the reductant concentration, this is the cobaltocene, the branches per thousand carbon began to significantly decrease in a corresponding manner, as almost linear. Went from about 114 down to about 88 over here. When we took a GPC of both of these polymer samples and compared it to a known linear polyethylene standard, this is similar to the trace that I showed you before, where this furthest top left is the linear polyethylene sample. The standard catalyst is the blue sample, and then our reduced species, the polymer generated from that, actually fell right in between the two. So to go one step further and try and provide some more information as to how these polymers actually, what these polymers actually were, we turned to quantitative C13 NMR analysis, where essentially we found that these two peaks correspond to sec-butyl branching on a polymer chain. And I have a picture of a sec-butyl branch right over here. And in the reduced species, they're not really present anymore. And the reason that this is significant is because this is the smallest form of branch-on-branch structure that can be identified via NMR. So this is actually the beginning of a hyperbranch structure being formed, and we've been able to actually eliminate this using this reduced catalyst. If we take a look at the other types of branches that can form, just a few are listed here, the methyl, propyl, butyl, and also the sec-butyl. All of these branches actually tend to decrease over the, as we increase the reductant that's been added. So all in all, we were able to decrease all of the branching types and specifically almost eliminate the branch-on-branch structure, which is the beginning of the hyperbranch topology where you can lead to extremely flexible and adhesive-like materials. So next, we needed to figure out what exactly this reduced catalyst looked like and why it was able to modulate polyethylene branching. So we were under the impression, because of some previous reports that had been published, that this acenaphthene-quinone backbone can actually delocalize the electron. And we enlisted the help of Professor Sharani Roy and Dr. Jesse Kearns to help us figure out what exactly this species was, as well as why it was modulating the density. And through using some experimental techniques that the EPR and the magnetic susceptibility, as well as their DFT calculations, we found that once we added the electron to the system, we actually got an EPR of 2.3, and that agreed with the calculated from the DFT calculations, which corresponds to nickel 1, as opposed to the ligand being actually delocalized through the backbone. Now, this was surprising because all of the other literature precedent had told us that it shouldn't have been this way. But then we thought, well, this isn't actually the active species anyway. So once we add MAO or TMA to the system, we found that it in fact did shift to the backbone, and this was favored in the DFT calculations, as well as from the experimental EPR, which agreed with the calculated EPR as well. The EPR of 2.00 represents an organic-based radical as opposed to the nickel-1 based radical. So next, we needed to figure out why this worked and why this modulated branching. So we obtained two energy profiles for both the reduced catalytic species and the native catalyst. And what I have listed here is essentially the pathways leading towards branching and the pathway leading towards a linear polymer chain generation. Now, as you can see from the native catalyst, the branching and the linear catalytic species have a negative 25.4 and negative 25.1 downhill in energy. So they aren't significantly different from each other. However, in the reduced catalytic species, we actually found that it was negative 19.9 to negative 23.7. So it was actually 4 kcals in energy lower to go towards the linear pathway than it was to go towards the branching pathway. So we actually created the system in which it was more favorable to make the linear polymer. So next, we wanted to figure out how does this system actually affect larger olefins, and in our specific case, how does it affect hexene? So we ran the similar polymerization trials that we did for ethylene, and we found that in the standard catalyst state, it's almost completed by around 1.5 hours to 2 hours. It didn't actually take that long to reach completion. But when we reduced the catalytic species, it took about 6 hours to reach the same completion rate. And if we analyze the polymers in each of these cases, the yield was the same, the molecular weight was about the same, the branching was the same. These are all very hyperbranch structures. But the rate had dropped significantly. So we thought, okay, the turnover frequency with ethylene we knew was constant from our previous work, but the hexene is significantly lower. So what happens if we copolymerize these two things together, and can we still get the same results? So we ran 3 separate trials where we have added 0 equivalents of reductant, half an equivalent, and then a full equivalent for the copolymerization of ethylene and hexene. And we found that, again, we saw a decrease in branching as we increased the equivalence of reductant. And specifically, the decrease for butyl branching was much, much larger than the others, which would make sense if the hexene, which should have 4 carbons other than the 2 that are involved in the backbone, was being incorporated less. Now, if we looked at the other polymer results for these 3 samples, we found that the branching, like I'd mentioned before, indeed went down. The yield went from 3.2 to 2.1 grams, so that's a significant decrease. But the ethylene consumed was about the same in each of the 3 scenarios. So what in fact was happening was the hexene consumed went from 1.3 all the way down to about 0.3 as we increased the equivalence of reductant. So we in fact were creating a system in which we could decrease and change the comonomer incorporation rates. So finally, we wanted to take all of this that we had learned and try to apply this to develop our own catalyst that could be redox active. And we wanted to, one, include the acenaphthene-quinone backbone that we knew was already redox active, but we also wanted to add something at these R2 groups because of the work that we had seen from Guan before. We wanted to make something that would be electron donating so that these polymers would be more linear. because every one of the polymer samples that we generated to begin with were all very low density. So we weren't actually getting any different types of plastics, we were just changing the branching content and showing the proof of concept. These R2 groups could also provide an additional opportunity for another redox active site. So with this in mind, we set out to synthesize our own catalysts, and we chose to synthesize 3 based on the Brookhart catalyst that he had released in 1995, and they all used essentially just different backbones. And condensing this iodinated aniline onto each of these diones, and then we achieved this diamine here, followed by a double Sonogashira coupling to give the ferrocene modified ligand that I have shown here. Now, some of you that have done organometallic synthesis might ask why we would try and do a double Sonogashira coupling, and that's because, like most chemistry, we tried it the other way and it didn't work. If you try and condense this ethynyl ferrocene aniline onto this dione, it just doesn't work. So we tried this double Sonogashira, and sure enough, that actually works. So once we got this ligand, we then metallated with nickel dibromide, and we were able to get this crystal structure thanks to some help from Gaia and Dr. Jenkins' group. And it dimerizes in its crystal state. As you can see, here's one nickel center and here's the other. And this is actually the same crystal structure as Brookhart's original catalyst that was released too. It does the same dimerization when it's in its crystal state. So then we moved on to cyclic voltammetry to try and see if these had oxidation and reduction potentials. And sure enough, every one of them actually has a peak that corresponds to the ferrocene that's in the backbone. However, only this acinate-quinone backbone shows a reduction potential, which is what we would expect, because these backbones aren't large enough to stabilize the additional electron that we would be adding to the system. So then we tried to do some preliminary polymerization results, and we found that regardless of catalyst 2, 3, or 4, and that's the acinate-quinone backbone, the methyl backbone, or just the hydrogen back there, the yield was significantly decreased, as well as the branching went dramatically down, especially if you compare it to what Brookhart's catalyst was originally. That was 114 branches, all the way down to 40 for the exact same backbone with the ethynyl ferrocene moieties. So we did decrease the branching significantly like we had hoped we would. So then, because of the very high yield and the moderate branching content that we achieved with acinapthene catalyst, we focused on it for the rest of our polymerization results. And we found that if we were to take our catalyst in its native state, we would produce very low density polyethylene. This was the 40 branches per 1,000 carbons that I showed before, and that has a density of about 0.9. And this is similar to a trash bag type material. This is very flexible. Now, when we add one equivalent of reductant to reduce the backbone, we drove the catalyst to produce only 9 branches per 1,000 carbon, and it went all the way up to a medium density polyethylene, which is similar to the flexible but still fairly rigid hosing that I showed on the first page. Now, when we added in 2 equivalents of oxidant to try and oxidize these ferrocene moieties on the outside, we were not able to get any results that were different from the native species, so it actually didn't work. And we believe that is because the MAO that we have to use as an activator actually is re-oxidizing the ferrocene back. So that aspect of the project kind of failed. But the other part worked, so that was still pretty exciting. So to sum all this up, redox active ligands are a fairly effective tool for tuning polymer microstructure and even controlling their branching content, the polymerization rates for larger olefins, and they can be used to even modulate polyethylene density as well. With that, I'd like to thank the Long Research Group, and special thanks to my undergrad Sang and Dr. Reinhardt for starting the project, as well as Dr. Roy and Dr. Kearns for their help on the project and for the computational work, and then Dr. Gaia Elpitia and Dr. Jenkins' group. Thank you.
I guess 1 or 2 questions that anyone have? I have.
Yes.
So in your theoretical study,
Mm-hmm.
you should only thermodynamic levels of the various energies of the various kind of semi-stable intermediates, right?
Okay, yes, yeah.
But isn't the polymerization kind of governed to some extent by the energy barriers between them? Or did I misinterpret your diagram?
Let me see if I can pull up. So here. So can you... So these, if I'm not mistaken, now I'm not a computational chemist, but I believe that these are intermediates and not transition states. So to try and answer your question, this was the preliminary work that we did, which just showed the delta E values. And the additional work that we found later, they're in the process of calculating transition states now, and they're also agreeing with what we had hoped. But yes, you're right.
All right, we have another seminar, so let's move right along. And this question from Dr. Mays.
Good luck, man. Thank you. There you go. That's still left on.
All Untitled multigraft Copolymer super elastomer will be presented by Velu. So Velu is a graduate student in Professor Mays group, and Professor Mays is not on the campus today, so I will briefly introduce him. Velu received his BS in chemistry from Chirin University, China in 2012, and he joined Professor Mays group in 2012 spring, and he has been working in living area and polymerization area. So he has been trained in glass blowing and high vacuum area and polymerization technique very well. And other than that, he is interested in different kind of membranes for water and gas purification and thermoplastic elastomer, different kind of cement material. So let's hear his presentation.
Thank you, Priya. It's my great honor to be here to introduce our work on the acrylic multigraft Copolymer thermoplastic elastomer. And since Dr. Mays is retiring and our lab is closing, first I'd like to introduce our hot research on anionic polymerization. The reason I use hot here is because we are not only the chemist, but also the glass blower, so it's very hot. And the main equipment for our use for anionic polymerization is this kind of high vacuum line. With the combination of the diffusion pump and the mechanical pump, we can reach a very high vacuum condition to remove all the moisture or oxygen or other impurities to reach the strict requirement for anionic polymerization. And by glass blowing, we can make this kind of different glass apparatus ourselves for different use, including for separation, for dilution, and for different reaction types. This apparatus looks very cool, but also looks very complex, so it needs very specific skills that normally we need to be trained for several months to gain this skill. So why do we need to gain this skill and to use anionic polymerization to make our product? It's because now, although there are many different kind of living polymerization, but anionic polymerization is still the only one that can accurately make polymers with controlled molecular weight and with very narrow polydispersity. And also, anionic polymerization is the only one to reach the non-terminating the living property even with the molecular weight as high as several billion kilograms per mole. Because of these advantages of anionic polymerization, it is a great candidate to be used for the design of complex polymer architectures. So let's go back to our topic today, the thermoplastic elastomer. From our daily life to the medical use, from the automobiles to mobile phones, we can find thermoplastic elastomer everywhere. The physical cross-linking structure make any changes by hitting reversible. This greatly improves the processability of the material and make the material recyclable. During the production, there is no need to add any compoundings and less energy to make the material with well-defined structure. Based on these advantages, the global market of thermoplastic elastomer has been increased in the last several years. Let's have a look at how thermoplastic elastomer work with the example of this one of the most commonly used Styrenic thermoplastic elastomer, this tri-block polymer of polystyrene, block polyisoprene, block polystyrene. The rigid block polystyrene can be used due to the thermodynamic incompatibility. The rigid block can be used to form the physical cross-linking junctions to provide the mechanical strength of the material. And the elastic block can form this kind of elastomeric matrix to provide the elongation property of the material. So this kind of Styrenic thermoplastic elastomer has been widely used because of its low cost and good phase separation behavior and tunable mechanical property. However, the medium block composed of polyisoprene or polybutadiene has the vinyl group, which is vulnerable to the oxidation and UV degradation. So it's not so chemically stable. Also, for the polystyrene, its glass transition temperature is only 100 degrees Celsius and is miscible with the polydienes. This makes the upper surface temperature always lower than 100 degrees Celsius, which is not so preferable not so preferred in the industry. So, on the other hand, acrylate-based thermoplastic elastomers can get rid of all these solutions because of the all saturated backbones. Also, acrylate-based thermoplastic elastomers can give us some extra bonus, including the excellent adhesion and good optical transparency and good oil resistance. However, the mechanical property of acrylate-based thermoplastic elastomers is always disappointing because of the term called the entanglement molecular weight. The entanglement molecular weight of this kind of acrylate-based thermoplastic elastomer is always much higher than the polydienes. The entanglement molecular weight, in definition, it means the molecular weight between the temporary entanglement junctions. So with the same molecular weight of the polymers, with a higher entanglement molecular weight, it means you will have less entanglements. In this way, the mechanical property is always much weaker as compared to Styrenic thermoplastic elastomers. So our work is focusing on how to improve the mechanical property of acrylate-based thermoplastic elastomers. And here this is the several examples for acrylate-based thermoplastic elastomers. For Ackermann's nano strings, they always has the elongation lower than 500%, and the mechanical strength always lower than 1 megapascal. For another kind of acrylate-based thermoplastic elastomer, Curare successfully reached the mechanical strength as high as around 20 megapascal. But for this product, its elongation is only 140%. In this way, we rather call this one plastic instead of the elastomer. And for other products, the elongation is still around or lower than 500%, and the strength is also much lower than the Styrenic thermoplastic elastomers. And for Styrenic thermoplastic elastomers, its elongation can be as high as 1200%, and its mechanical strength can be as high as 33 megapascal. So this is a much larger difference. So our strategy is to design these complex polymer architectures. Different kind of polymer architectures has been studied and developed, including these linear type block polymers, cyclic block polymers, polymer stars, hybrid branch polymers, polymer networks, these Graft Copolymers and multigraft polymers, and H-shaped block polymers. As compared to the linear block polymers, polymer with complex architectures can give the much lower hydrodynamic radius. Also, it can give lower melt and solution viscosity, and with improvement on the crystallinity, solubility, and the rheological behavior. Moreover, the complex architecture can also has a better ability to tune the morphology. For example, as reported by Dr. Pochen and Dr. Mays, this kind of tri-arm stars composed of one polystyrene chain and two polyisoprene chains can phase separate into the cylindrical morphology with very long range order. So the Styrenic multigraft copolymer thermoplastic elastomer has been reported before with the polyisoprene as the main chain and polystyrene as the sidearms. This multigraft copolymer can reach the mechanical strengths comparable to the commercial linear type Styrenic thermoplastic elastomers, but with the much increased elongation even higher than 1,500%. And even when this sample was stretched to 14 times, it can still recover to its original shape with only 40% strain loss. So by the combination of this much improved mechanical elongation higher than 1,500% and very good strain recovery, they name this material as super elastomer. The preliminary work of acrylic-based thermoplastic elastomer was done by our lab senior, Dr. Andrew Goodwin, using polybutyl acrylate as the main chain and polymethyl methacrylate as the side chains by graft-through methodology. This PMMA macromonomer was synthesized by Anionic polymerization using hydroxyl-protected unbutyl lithium as the initiator. After the deprotection of this hydroxyl group, it can be linked with the acrylaryl chloride to make the final macromonomer. However, this approach requires very complex operations. For the linking reaction itself, it needs a very long reaction time and with very limited conversion. In this way, it's very hard to make very large amounts of the polymer samples to reach the requirement for tensile study. As a modification, we find this new initiator called N-isopropyl 4-vinyl-benzoamine, in short PVBA. After it activated by the secbutyl lithium, the formed nitrogen ion is too weak to attack this styrenic vinyl group, but strong enough to initiate the methacrylates. In this way, the macromonomer can be synthesized by Anionic polymerization with 100% conversion and the reaction time as short as 1 hour. The initiator PVBA can simply synthesized by the 4-vinyl benzyl chloride with isopropylamine. And after the activation, that is the combination of secbutyl lithium with the PVBA, it can form this kind of light yellow color, which can turn to the deep yellow color after 30 minutes, which means the completion of this activation. Then lithium chloride was added to the system to avoid the attack of this nitrogen ion into the carbonyl group. This is a side reaction that will make the polydispersity very broad. And it will form this kind of green color. And after the addition of the MMA monomer, the solution color disappeared with the increase of the viscosity, which is the common phenomena for living PMMA polymer chains. By Anionic polymerization, the PMMA Macromonomer was successfully synthesized with the PDI polydispersity even as low as 1.02. And by NMR, we demonstrate the intact vinyl group after the polymerization. And this PMMA macromonomer was used to copolymerize with butyl acrylate by controlled radical polymerization to make the final Graft Copolymers. And from the GBC trace, we can see the clear shift from the PMMA macromonomer to the final Graft Copolymers with even no remaining of the macromonomer. And the composition of this butyl acrylate and MMA blocks were determined and calculated by the proton MR. And 4 different polymer samples were synthesized with the different molecular weight of PMMA side arms and its volume ratio. From both the differential scanning calorimetry and the dynamic mechanical analysis, we can see the 2-step shift with the change of the temperature. This 2-step shift, this 2-step transition is the indication of the microphase separation behavior. Also, with as compare of these glass transition temperatures with the glass transition temperature of the homopolymers, it has the very similar glass transition temperatures. So it means this little shift of both glass transition temperatures means little phase blending existence in the final block copolymer, which means the microphase separation behavior of this final block copolymer are very strong. And the microphase separation behavior were directly observed by the atomic force microscopy and demonstrated by the clear peaks in the small angle X-ray scattering. With the increase of the molecular weight of PMMA chains and its volume ratio, we can see the improvement of the microphase separation behavior. Among all the polymers, the Graft Copolymers with PMMA molecular weight of 29.3 kilogram per mole and its volume ratio of 33.8% gives this worm-like morphology, which was also roughly demonstrated by the Sachs curves. The stress-strain behavior of these materials were characterized by the uniaxial tensile testing. With the volume ratio of the PMMA as high as 33.8%, the material reached the mechanical strength as high as 10.8 megapascal, but with the elongation still around 500%. Then among all the polymers, with the molecular weight of the PMMA of 29.3 kilogram per mole and its volume ratio of 9.3%, it gave the stress as high as 2 megapascal and the elongation higher than 1700%. So this is much beyond the commercial product with the mechanical strength always lower than 1 megapascal and the elongation always lower than 500%. When this specimen can be stressed to even as long as 12 times to its original length, and it can still recover to its original shape with only less than 15% of the strain loss. By the combination of this elongation higher than 1700% and its very good strain recovery, the acrylate multigraft copolymer superelastomer was successfully synthesized. The further improvement of the mechanical strength of the material were performed by the introduction of extra driving forces, such as the hydrogen bonding, ionic bonds, coordination bonds, or host gas interactions, which can be used to improve the microphase separation behavior of the material. However, different results were reported before. For Thermoplastic and Copolymer, they reported the introduction of the hydrogen bonding, the ionic bonds, and coordination bonds can lead to the increase of the tensile strength, but with the decrease of the elongation. For another work, with the introduction of the hydrogen bonding, the mechanical strength can be decreased, but the elongation can be increased. As a demonstration of the hydrogen bonding, we synthesized this graft copolymer of polybutyl acrylate, graft polybutyl mesacrylate, using the same strategy for the graft copolymer of PVA graft PMMA. After that, the T-butyl mesacrylate was partially hydrolyzed by hydrochloric acid to form the mesacrylic acid. In this way, we can introduce the hydrogen bonding. From the first derivative of DS curves, the original graft copolymers show the glass transition temperature of around minus 31 degrees Celsius. After the hydrolysis, a new peak at minus 42 degrees Celsius, which correspond to the glass transition temperature of butyl acrylate, were shown. This means the improvement of the microphase separation. And from the tensile test, when the hydrolysis degree reached 54%, it gave the mechanical strength as high as 64 megapascal, which is much higher than original graft copolymer with only 1.4 megapascal, with the elongation still higher than 500%. When the hydrolysis degree is 42%, the mechanical property is 68 megapascal, with the elongation higher than 1,000%. Even with a very slight hydrolysis, as around 16%, the material still shows a 2 times increase of the mechanical strength, with the elongation higher than 1800%, for which we can still call it super elastomer. The further modification of this material can be were performed by the introduction of sodium hydroxide to change the methacrylic acid into the ionic type. In this way, we introduced the ionic bond. So for the hydrolysis degree of 42%, after the introduction of ionic bonds, it showed elongation, it showed the mechanical strength as high as 15.2 megapascal, with the elongation higher than 700%. When we compare the mechanical strength at 500% with the introduction of H bond, it showed the increase of around 19 times for the mechanical strength, and show the further around 3 times higher increase of the mechanical strength by the introduction of ionic bonds. So other than the use for thermoplastic elastomer, this PVBA is a powerful candidate for the design of complex architectures. In our preliminary work, the macromonomer was linked with the living PMMA with the living PS chains to form the coupling diblock copolymers, which can be seen from the color change from the deep orange color into the red color. After the end cap with the DPE to decrease the reactivity of the living chain ends, the third chain of the PMMA can be further grown. From the GPZ trace, we can see the successful production of these triumph stars with around 20% remaining of the coupled diblock copolymers. With similar strategy, the equilateral chloride can be used to couple with after the coupling after the coupling reaction to form this double-tailed macromonomer. After the copolymerization with butyl acrylate, it can produce these double-tailed graft copolymers, which can be another thermoplastic elastomer. When we use difunctional initiator to couple the macromonomer first, followed by the growth of the second kind of monomer, these tetraarm stars can be polymerized. If we use the difunctional initiator to polymerize styrene first, followed by the coupling reaction and the growth of another monomer, this kind of H-shaped block polymer can be synthesized. So as a summary of our work, first, we successfully synthesized the graft polymer of polybutyl acrylate, graft polybutyl methacrylate, with a very simple operation, which showed very clear two-step transitions from both DSC and DMA. And both AFM and SEX showed a very distinct microphase separation behavior. This material can give the elongation longer than 1700% with very good strain recovery, for which we can conclude that the successful polymerization of all acrylate multigraft copolymer superelastomer. With the further introduction of the hydrogen bonding and ionic bonds, we can see the further improvement on the mechanical property of the final graft copolymers. And this the PVBA initiator is a powerful tool to synthesize the complex architectures, including the double-tail, single-tail, and double-tail multigraft copolymers, the triarm and tetraarm stars, and even this kind of H-shaped block copolymers. These works are guided by Dr. Nangu Kang, Dr. Kunlun Hong, and Dr. Jimmy Mays. And the characterization methods were helped by Yang Yang, Wei Yu, and Jia Hua. And I received a lot of, and I want to thank Dr. Andrew Goodwin for the share of many experience on acrylic thermoplastic elastomers. And thank you for all your attention.
So we have a few minutes for questions. Got to be some polymer students out there. Questions? I have a question. Do you see, when you make your hydrogen bonded, you have amines there, you have carboxylic acids. Do you see any zwitterite formation? Do you have any idea?
Okay. Yeah, we have an amino group here, but you can see for this kind of, for this polymer, for the, I can show the structure here. For this structure, we have an amino group here, but for the branch points, we only have 5.7 branch points. It means for this kind of huge polymer chains, we only have 6 amine there. So it's a very small amount. It will not affect any this kind of carbonic acid groups. So we didn't see any kind of aggregation or any other interactions.
And in the hydrolysis, you have both butyl esters and also butyl esters?
Yes.
So you can selectively hydrolyze these?
For the hydrolysis of polyacrylate or polymersacrylate, with different conditions, you can hydrolyze different kind of these functional groups. With the acid condition, it is mainly hydrolyze this kind of butyl group. With the basic condition, it can hydrolyze this kind of primary carbon. And also PMMA can also be hydrolyzed if you use some catalyst and basic condition.
Questions? Well, let's thank our 2 presenters again.